Okay, hello everyone, welcome back. So now let's talk about molecular orbital theory. So, in my opinion, a very sometimes hard to rack your brain around molecular orbital theory. So let's just jump into it. All right. So first, let's go back to when we talked about the sulfur dioxide molecule SO2. The valence bond model couldn't adequately explain the fact that the molecule contains two equivalent bonds with a bond order that's between a single and double bond. Okay? So the best thing the model can do or come compromise is suggest that sulfur dioxide is a mixture or hybrid of the two Lewis structures that can be written for the molecule. Okay? So we can actually overcome this problem with a different model called different model of bonding based on orbitals that don't sit on one atom, but they encompass the whole molecule. And that's called molecular orbitals. So this model was created because it's better at predicting some properties when the valence bond model fails. So they kind of coexist with each other. So in this class, we will focus on the molecular orbitals for the most simple molecules to aid our understanding of the very basics of molecular orbital theory. Okay, so if you venture into more chemistry classes, you'll learn more about molecular orbital theory, especially if you take physical chemistry. But for this class, we're just going to cover an introduction to the topic and how it can explain some bonding properties that the valence bond theory cannot. Okay, so we will focus on the simple diatomic molecules: CO, NO, H2, O2, N2, Li2. So can bonding exist between helium atoms or metal atoms? We're going to use this model to help predict that. Okay. All right. So much like the hybrid orbitals were obtained by combining atomic orbitals, molecular orbitals are also obtained by combining the atomic orbitals that are now characteristic of the whole molecule itself and not just on an individual atom or atoms, like I said before. Okay, so let's consider the H2 molecule as our prime example. One of the molecular orbitals in the H2 molecule is constructed so it's very similar to how we've made hybrid molecules, right? So there was an orbital that was a combination or the sum, and then there's one that are the difference between the orbitals. So we get two possible solutions for hybrid orbitals. It's the same kind of thing for molecular orbitals. So we add the mathematical functions for the two 1s orbitals, and the two solutions we get, if we put two inputs, we must get two outputs. So they come together to form the molecule, okay? And then we get the other molecular orbital by subtracting the functions from each other. So the result is in this diagram here. So here's the interaction between a pair of 1s atomic orbitals on neighboring hydrogen atoms. So we get the summation is an orbital of lower energy. That's called the bonding or sigma bonding molecular orbital. And then the one that gets us higher in energy, that's a sigma star anti-bonding orbital. Okay, so the interactions, we get a energy interaction that's favorable, the bonding interaction, and then we get an anti-bonding interaction that's not favorable. Okay, so let's go over some of these terms. So a bonding molecular orbital, so electrons that are placed in this orbital, they will spend most of their time between the neighboring atoms. So that's why it's called bonding orbital. And you can see in the picture, it has an orbital that encompasses both of the nuclei. So that's called a bonding molecular orbital. Okay? So we call this a sigma molecular orbital because it's bonding. Then anti-bonding is the opposite of that. Electrons placed in this orbital, they're going to spend most of their time away from each other, and so they're isolated nuclei. So electrons that are spent here don't want to bond, and when you put electrons in this orbital, you actually cause the molecule to become unstable and cause bond breaking or reaction events to potentially occur. Okay? So they spend most of their time away from the region between the two nuclei. So we call this a sigma star molecular orbital or anti-bonding. Okay? So if since we're having trouble wrapping our brains around that, just think of it this way. Bonding orbital, lower energy, favorable. Anti-bonding, higher in energy, does not want to bond. So it's unstable. So it's a destabilizing orbital. So electrons don't like to stay there. Okay. So a couple things to note. When two atomic orbitals are combined, we get two molecular orbitals. Orbitals are conserved. Energy is also conserved because you have an orbital of lower energy, then you have an orbital of higher energy. And when they combine energies, you get back to your starting point, which is two nuclei at the center there and the black and white spheres. Okay? So the lowering of energy of the bonding molecular orbital, typically it's equal to the raising of the energy of the anti-bonding molecular orbital. So we say the energy of these orbitals are raised and lowered from the energy of the isolated atomic orbitals by the same amount. So there's an equal contribution there. So it's always equal to 0. Okay. Now let's go over some vocab so we can understand some terms here. All right. The sigma bonding molecular orbital concentrates electrons in the region directly between the two nuclei. Okay? So therefore, placing an electron in that orbital, does it stabilize or destabilize the H2 molecule? Well, if it's making electrons more happy, it's putting it near more nuclei, that means the energy is probably going to lower, so it's going to stabilize the H2 molecule. Okay? Since the sigma star molecular orbital forces an electron to spend most of its time away from the area between the nuclei, the placing an electron in that orbital makes the molecule less stable because it's now moving further away from the other nuclei that could potentially stabilize it from the interaction with the nucleus of the other atom. So that's what we call less stable. All right. Now, how do we fill the ML diagram? So you may have seen these ML diagrams. You may be expected to draw one. So let's go over these together. Electrons are added to molecular orbitals pretty much in the same way we did electron configurations, where we filled each atomic orbital according to energy level. So electrons are placed one at a time, starting with the lowest energy level. Okay? Starting with the lowest molecular orbital. So we see here on the sides here, those are our atomic orbitals. When we combine them, we get a sigma bonding molecular orbital and a sigma star bonding molecular orbital. So those two atomic orbitals combine to make two molecular orbitals. Okay? So for the hydrogen atom or molecule, two electrons are associated with a pair of hydrogen atoms, and they're going to first be occupy the lowest energy orbital or molecular orbital, and that's the sigma bonding molecular orbital. So just like the regular orbitals, only two electrons can fill each single molecular orbital. So both of those electrons are going to pair up in the sigma bonding molecular orbital. And since both electrons are in that lower energy bonding orbital, that's why the H2 molecule exists as HH. And if we had populated the anti-bonding, that might not be the case because there's no net benefit to occupy both. So you're better off just being isolated atomic single hydrogen atoms. But the fact that H2 exists as H2 kind of gives us insight based on the bonding predicted by this model. So this is how we use MO theory. Okay? All right. All right, so that's how we would draw a typical molecular orbital diagram. So you might be expected to fill one out, or you know, reproduce one to analyze the bonding mode of a hypothetical element. So it's important that we know how to fill these out. Okay, so let's move on now to a situation where we have now not hydrogen, but now we're talking about helium. Okay. So here's this sentence here that kind of summarizes the outcome of that first diagram. So the molecule is more stable than having two hydrogen atoms isolated from each other. So that's why H2 exists as the H2 molecule. All right, so this model can also predict why H2 helium is not a molecule, and we just call it helium atoms. So helium exists as just a noble gas. One atom, helium is represented by just one atom of helium. So we take a look at this molecular orbital. So helium has 2 electrons. So if we're trying to make helium-2, 2 helium atoms are going to come together here, and you see that we have 4 total electrons now. So when we populate the molecular orbitals, we're going to get both the sigma bonding and sigma anti-bonding orbitals completely filled. So now there's no net benefit for H2 to exist, because now the energy you gained by putting electrons in the molecular orbital, the bonding one, is negated by occupying electrons in the higher anti-bonding orbital. So it's a net effect of 0, so it's better if helium doesn't bond. Okay, so combining a pair of helium atoms with the 1s2 configuration would produce a molecule with pairs of electrons in both molecular orbitals. So in this case, the total energy would be essentially the same. Will be essentially the same. That's what as in front of here, as the energy of a pair of isolated helium atoms. So there will be no force to hold a helium-2 molecule together. So that's why helium doesn't exist as He2. It's helium, just one single helium atom. Okay? All right. All right, next let's talk about a little more complicated situation here. So how about molecular orbitals for the oxygen atom? All right, so when we're writing the MO diagrams for atoms in higher energy levels, we now form MO or molecular orbitals from p orbitals. So in this case, we have to define the z direction. So we're going to define that as the axis between 2 atoms in the O2 molecule. So we get 2 types of molecules here. Sigma molecular orbitals, sigma, like a sigma bond. And then we get, so those bonds come from direct overlap of the p orbitals on the z-axis. And then pi molecular orbitals. So we get pi bonds as well, formed from p orbitals that are perpendicular to the axis. So in this case, we get 2 sigma bonding orbitals, sigma 2 star 2p antibonding, and sigma 2p bonding orbitals right here. So when the bonding orbitals combine, so you see here, the orbitals, it's kind of their wave functions, right? Like we talked about in chapter 7. So when they have the same sign and it's constructive interference, you're going to get a bonding interaction. And you see here, the 2 lobes that interact now get bigger. And now if you have destructive interference, we see here that the orbitals now, they kind of cancel each other out instead of combining to get larger. So that's how you can think about sigma bonding and sigma anti-bonding orbitals, okay? Okay, so that's when they are combined on the same axis, but now we have pi orbitals. So if pi orbitals, they have side-by-side overlap, like in this picture. So if two waves interfere constructively, they're going to form a bonding molecular orbital. See at the bottom here, the sides of the lobes have kind of combined in size. And then if they don't combine, they're going to point away from each other. So you see here, now there's what we call a node here. So that's where the orbital changes sign. And that happens in anti-bonding because now you're going to have two instances where it changes sign here and here. So that indicates that there's no bonding, so no interaction between these two orbitals. So there's no bonding effect, higher in energy. Okay? Here we go. All right. Okay, so those are some molecular orbitals for the 2p 2p orbitals when they combine to make molecular orbitals. All right. So you see here, now we can construct the molecular orbital diagram, and you can see here it's a little more complicated than than we think it needs to be, right? And that's because only one p orbital will be involved in sigma bonding, like we saw above in our picture. And then the other two p orbitals available are going to be pi orbitals. So that's why there's two sets. Pi x in the x direction and pi y, and then the anti-bonding orbitals for the pi orbitals. So they usually orient themselves in this fashion. Since the pi bonds are not a result of direct overlap of atomic orbitals, they are not. The energy difference between the p orbitals is less because they have a smaller interaction here. Okay, and then below it is the typical picture we see for the s orbitals, 2s, then we have the 1s. So we can actually fill these orbitals here based on oxygen's configuration. Okay. So let's fill out the molecular orbital diagram for oxygen. So oxygen has 6 electrons each. So we should have a total of 12 electrons, okay? So 1s. So each oxygen atom will have a complete 1s, a complete 2s. So when we fill the orbitals, we're going to see that they're going to populate like so. And then now we go up to the 2p orbitals. So oxygen has oxygen doesn't have 6 valence electrons. 6 electrons, has 8, right? So when we're doing molecular orbital diagrams, we want to consider all the electrons for oxygen. So now it's going to have 4 additional electrons in the p orbitals. 1, 2, 3, 4. 1, 2, 3. 4. Right, so. Okay, so now let's fill out these electrons. So we have 8 total. 1, 2, 1, 2, 3, 4. So that's 6, 7, 8. Okay, so see here, we didn't fill up all the atomic orbitals or the anti-bonding orbitals. So there is still some net benefit for O2 molecule to exist. So that's how we would fill these molecular orbitals, okay? Okay, so let's go over this. So, the interaction between the two pz atomic orbitals that meet head-on, so that's going to be a stronger overlap. So stronger overlap than the interaction between the p2x or p2y orbitals that meet side by side or edge on. So as a result, the difference between these energies, sigma 2p and sigma 2p star orbitals, is larger because there's more orbital overlap. Okay. Larger than the difference between pi x and pi x star, pi y and pi y star orbitals. Okay. So looking at this orbital now, the diagram, we can write the electron configuration for the O2 molecule by just using an abbreviated form of electron configuration. So for oxygen, we would say, all right, so you can write the sigma 1 star, but you don't have to. But we could anyway, so I guess I forgot to erase this. So sorry about that. Let's just redo it. So let's look at our diagram. So we have 2 electrons in the 1s and 2 electrons in the 1s star. So we're going to write sigma 1s squared, sigma star 1s squared, okay? And then we go back up to here. We have the 2s and 2s star. So we're going to write sigma 2s squared, sigma star 2s squared. Okay. And then we keep going. Now we have the 2p, the pi x, pi y, then the pi x star, pi y star. Okay. So we write this as sigma 2p2, pi x2, pi y2, and then lastly pi x star 1, and then pi y star 1. Okay, so that's how we could write our electron configuration based on the molecular orbital diagram. Okay, so we'll stop the video here, and next time we'll pick up on how this molecular orbital diagram can differ for different atoms or elements across the periodic table. Okay, so I'll see everyone in the next video.